Right, we're recording. So we've come as far as if we'll take questions in the end if there are any. Phase 3 was extended, yes. Oops, that's not what I meant to write. Predictive table-driven LL1 parsing. Now, remember when you implemented the basically all of the functions in phase 3 at the very top that sort of had to climb the class hierarchy, and because it's a recursive data structure, you implemented that hopefully in a recursive manner, because trying to do it in an iterative manner is really, really difficult because you got to maintain your own stack, right? Now, when we have a recursive descent parser, as we've seen, that's recursive. So it uses the recursion stack. Yes, phase 3 is extended. Be on time next time. But we could mimic that stack by hand, So for example, if we have a recursive descent parser, that might have something like parse E, which says parse T, etc. Then we will have our call stack, and we will have parse E, parse T, and then whatever comes after that. Now, if I look at the grammar, that looks something like E goes to T E prime, E prime goes to plus T E prime or epsilon, and T goes to, should we just do the easy one here, like that, for example. Now, I could say that when parsing an E here, that's the same as parsing, I suppose if we fill in here, we get something like that. Well, actually, we probably don't. We get, let me redo that. Your call stack would look something like this. Some stuff, parse E, parse T, and then it would become parse E, parse E prime, and then it would look like that. So because in order to do an E, you got to do a T and an E prime. So we have the E there, we do the T first, then we do the E prime, and then we're done. So we can sort of mimic that on a stack in some way. So for example, actually, should we do that on another page? I'm just going to grab this. So if I start out, I'm going to just I'm going to lay down my stack because it's just easier to write things out this way. And let's say I have some input. I don't know, it's just ID. Oops. ID plus ID. And let's just say that I want to start with an E. Right. Now, if we were doing recursive descent, hold on. I don't know what happened. If we were doing recursive descent, we would say, right, we'll go look at the first sets, and then we'll say if ID is in the first set of T prime, then we would call parse T, and then we'll call parse E prime. But now, couldn't we say that here, in order to do that, so in order to match that to this, I got to match that to this. So what if instead I just said, right, instead of doing that, I'm going to match E prime and T. And note how I sort of swapped them around because we got to do the T first because we're doing left to right. Right. Uh, but so now I can say, well, I got to do the same with a T. So we still have our E prime, and then that T is an ID. And then I can say now, that and that is a match. Right. Well, what does that mean? Well, that means that we can sort of square those up and say, right, the rest of this stuff that we have left here now, that has to be generated by that. Okay. Now, which one of those two should I replace it by? Should I do that one or that one? Well, there's more stuff here, so doing that one would make the stack empty with more inputs. That would probably be a silly idea. And also, that starts with a plus, and there's a plus there, so that might make sense. So we probably go and do something that looks like this. So that becomes, that's supposed to be an E prime, right? Yeah. E prime T plus. But now that is a match with that. All right. So then we get E prime T. What's next? There's an ID, and T can become an ID, so we can just do that. I'm going to continue over here. So we have our E prime, and we have ID now. And, ta-da, match, match. There we go. So what next? Well, then that's gone, and we're back to just having an E prime. I don't have any more input, and luckily E prime can go to epsilon. So we're done. Now what we do in reality is we just sort of glue a dollar symbol there, 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 to sort of denote the bottom of the stack. And we put a dollar there. So if I can reduce my input to end of file while clearing the stack, you can sort of think of putting that end of file marker at the bottom of the stack. Then we manage to produce a derivation of the input string, and we can see that this indeed is a derivation because it says E goes to T, E prime goes to ID, E prime goes to ID plus T, E prime goes to ID plus ID, E prime goes to ID plus ID. So we did manage to mimic a leftmost derivation of the input string using a stack instead. And you can probably imagine that the algorithm, the parsing algorithm, is probably a set algorithm that just uses a different input depending on what the grammar looks like. So for example, if I asked you, look at this grammar, and let's actually just write down here, I'm going to just write down what sigma is, because it's plus, it's ID, and it's end of file. What if I asked you, if I have an E on the top of the stack, that means I'm trying to parse an E. So that means I got to pick one of its right-hand sides. What should I do if I see a plus? Well, I can start by asking, what's the first set of that? Isn't that ID? And since it's the only right-hand side, then if I see anything other than ID, then we're in trouble, right? Because we can't derive it. So if I see an ID, then we're good. If I see a plus, not so good. And if I see end of file, then we're in trouble as well. So there's really only, if I see an E, only one valid next look ahead on the input, which is an ID. Now the question, of course, is what should I do if I see an ID? Well, then you should take the next step in the derivation, the next correct step in the derivation. We can see that that's that one, which is pretty obvious here because there's only one right-hand side. But we did pick the right-hand side that had a first set that matched with ID. Okay, what about that? Well, now I have a T at the top of the stack. I should pick a right-hand side of T. Well, that's only ID, and I have an ID, so I can replace that by ID. Now I have a terminal on top of the stack that has to match the look ahead. If it didn't, then we'd never be able to derive the look ahead. And if we do get a match, then we can remove them and move on. So we can use the first sets of the right-hand sides to drive the replacement of the non-terminal on top of the stack, depending on what the look ahead is. And if I have a terminal on top of the stack, we can do a match, just like we did before. So we can think of a predictive parser in the following way. If I can do this so it looks nice. So this is my tokenized input. So this is oops. Right now, I'm in middle of class. Dr. Gawai says you have to think about your lives while I talk to him for 2 minutes. So be right back. Think about this. Right, I'm not being fired yet, so I get to stay for a little more. But I do have to just quickly forward an email to him. Right. So did you think about this? So what did we have? We had the input there. The input ends in a dollar. Shall we call that? We started. I don't know why I didn't start at A0, but I had A1. It doesn't really matter. And our stack. Well, we were going to put that dollar thing at the bottom just so that we know when we hit rock bottom. And in here we have a table, and I don't know why it's called M. It just is. So it's looked up based on a non-terminal and a terminal where where the non-terminal, just check that, there we go, where the non-terminal comes from the top of the stack. So basically we are saying, well, if on top of the stack I have this particular non-terminal, so in the case that we had here, if I had that particular non-terminal and I have that particular look ahead, which of the possible right-hand sides should I pick, if any of them? And this guy is the look ahead. And that lookup here is going to be some rule with the non-terminal on the left and a right-hand side with the look ahead in its first set, or an error entry, because it could very well be that the look ahead is not in the first set of any of the right hand sides, in which case we would do an error. So for example, if we go back and look at this one, what should I do if I'm trying to parse an E and I see an end of file? Well, end of file is not in the first set of that, so we should have an error. So let's do an example. Man, I'm popular today. That was Dr. Nazes. All right, so example, what, 412. Oh, and it's our good old friend that we just saw on the previous page. Just boiled down and changed a little bit, so we'll use f instead of t. E prime is still plus f e prime or minus f e prime or epsilon, and f is just an ID. Right, so let's see, let's make some notes over here real quick. Sigma is plus minus ID and dollar. And we need the first of FE, we need the first of plus FE prime, we need the first of minus FE prime, we need the first of epsilon, and we need the first of ID. And I think you can probably calculate those real quick. That's an ID, that's an epsilon, that's a minus, that's a plus. First of F is an ID, so that's just an ID. Right, there we go. Now we need a table that has all the non-terminals in the columns and all the terminals in, sorry, all the non-terminals going down and the terminals going across. So we need to draw a nice little table here with 1, 2, I'm going to see if I can do this so it looks nice. 1, 2, 3, 4, 5. So no, I couldn't do it so it looked nice. Yeah, that's good enough. And this one here is sort of a double line. No, that didn't work. So we need the non-terminals. We have E. We do that with proper handwriting. E, E prime, and F. And then how many columns do we have? Well, we have as many as we have there. So we need 4 nice looking columns. Almost the same. And we have plus, we have minus, we have ID, and we have dollar. Right. So now the question is, How do we fill that table? And what I want is, remember the following. If I'm trying to parse an E and I see a plus, which of E's right-hand side should go there? Actually, so for example, if I point it down to, if I point actually, let me point to here. This cell contains a rule. E goes to something. I'm going to put alpha with minus in the first of alpha, or error. So in theory, we should be able to fill this out now, shouldn't we? So if I'm trying to parse an E and I see a plus on the input, what should I do? Well, if I just annotate over here that this guy has a first set of ID, this has a plus, this has a minus, this has nothing, and this has an ID. Then again, I ask, if I am trying to parse an E and I see a plus on the input, what should I do? Well, you don't get a chance to do nothing. Unless you're doing an epsilon, I suppose. You gotta do one of these two things. So it's got to be either an error or it's going to be the right-hand side that has that in. Yeah, right. So we need an error here, right? We do that in red. Well, this one is fairly easy to fill in, right? Because ID is the only element of the first set of the lone one right-hand side that we have. So we know that if we can spell error, we can fill that in. And then since ID is in the first set of FE prime, that's the one we'll do there. Now what about E prime? E prime, I have 1, 2, 3 options. And we're going to get a little bit in trouble with that one there. But we'll come to that in just a second. So let's start with this guy here. Which of these columns, which of these cells should have E prime goes to plus FE prime? If any of them, well, some of them should. In the plus column, right? Yes, because that has a plus in the first set. And now note also, now you can see why these intersecting first sets are sort of important, right? Because what if this guy had a plus in? Well, then I would have two different things and I'd have to put two different rules in there, and then I wouldn't be able to make the correct choice. Right, so we need to, should we do that in a green? Do it in a forest green. So we'll say E prime goes to plus F E prime. And then similarly, we can probably do this. What about that one there? There are no epsilon columns. If you go back and you look at the recursive descent version of this one, how did we handle epsilon there? So let me just, I'm just going to rope this one here. And then I'm going to go here. Put it there. And then say, we'll just write the recursive descent and see what happens. If the look ahead is a plus, then match the plus, parse F, parse E prime, else if the look ahead is minus, match minus, parse F, parse E prime, else what? Well, nothing. Now we did talk about a slight change here. We said, or we could say if, so or for this entire thing here, if look ahead is in the follow of E. So in other words, the next thing on the input, can that follow E? Because if it can't follow E, then it couldn't be derived the way it is. So if the look ahead and follow E, then we're okay with an epsilon, else error, right? So those, do you remember this? These are the two options we have for handling epsilon transitions in a recursive descent parser. And the first one we looked at was just doing that. So if I wanted to mimic that in this situation, I can just put the epsilon ones in both of those. If I wanted to mimic this stuff over here, now we're going to have to calculate the follow of E. So I suppose we can do that as well. Let's see. What can follow E? Well, that's easy. Dollar. Right? So if we call this one here type 1 and type 2, then we could fill these in both ways. If we're doing it the type 1 way, or we're doing it the type 2 way. If we're doing it the type 1 way, then it's easy because it's just, hey, anything that's not filled in, so anything that didn't end up there and there, will end up here, and we'll just do epsilon transitions. So in the type 1 way, it's just E prime goes to epsilon, E prime goes to epsilon. In the type 2 way, where we are a little bit more conscientious about catching errors early, we said we'll only do it for the follow set, and the follow set is just the epsilon, and then down here we would get an error. So we can see that what happens in this situation is that we would just catch the error earlier, right? So instead of doing that transition, we would catch the error there. This one here will end up being the same. Now that bottom one there is super duper easy because it's just, well, if you can do it right, F goes to ID, and there we go. Now let's give it a whirl. So we'll write down in a second how to fill this one out using some formulas, but let's just actually try to do some parsing with it and see if it actually works, if we got it right. So there we go. Let's see, what string shall we try? Oh, we can try redo. Delete that one, and can I surgically come in here? And no, I can't. Yes, maybe I can. Maybe if I say don't erase the entire stroke. There we go. So should we use type 1 or type 2? Let's use the type 2 ones. I don't think we're going to need it, but right. So what do we need? We need a stack. We're going to start out with $E. We're going to need an input. We'll start with ID plus ID plus ID dollar. And then we'll use, figure out what rule we used. Right. So on an E, next input is an ID, E. On an ID, I replace that E by Fe prime. So we can say that M of E comma ID is E goes to, oh, it was F, wasn't it? F E prime. So we get dollar E prime. Remember when we replace a right hand side with more than one thing, that goes on in the opposite order because we need a left to right derivation. We didn't touch this at all. We just looked at the look ahead. So what should I do if I have an ID as a look ahead and an F on top of the stack? An F with an ID is replace the F by ID. All right. M of F ID is F goes to ID. Right, easy enough. E prime ID. Didn't touch this yet. But now I have a match. I want the light green here. That matches that. So we'll remove them. E prime plus ID dollar. Right. What do I do if I see a plus on the input and I want to parse an E prime? E prime plus, take that roll. All right, easy enough. M of E prime, comma, plus is E prime goes to plus F E prime. Dollar E prime goes away and E prime F plus is left on the stack. We haven't touched the input, but now, well, it didn't go quite the way I wanted. That and that is a match. So we get dollar E prime F ID plus ID dollar. What's M of F on an ID? Well, it's probably F goes to ID. So we get dollar E prime ID plus ID dollar. That and that is a match. So we get dollar E prime plus ID dollar. M of E prime on a plus. Again, it's that one and that one is plus F E prime. All right, that goes. So that goes and gets replaced by plus F E prime in reverse order. Get that? Haha, look at that. Plus, plus. The match. So then we're down to that and that. What's, oops, that's not an E, that's F ID. Note that whatever it is that I have here is always the top one there and is always the left-hand side there, right? So that's F goes to ID. Dollar E prime. We're running out of space here. ID dollar. Ah, but look, match, match. Then we have dollar E prime, dollar. And finally, M of E prime on a dollar is E prime goes to epsilon. So we get dollar, and we are done. So that's actually super simple to do. And you can see, if I provide you this table here, then you just have to be able to do these replacements. So pop the top of the stack, replace it by the left-hand side in reverse, and do matchings. And if you look at algorithm 9, that is exactly that. So we We keep going for as long as we need to. We take a look at the top of the stack. So what we do is we say, all right, that's the top of the stack. And then we say, well, is that a terminal or is it a non-terminal? If it is a terminal, then if the terminal, so that's these green things, if they match and they're both $, then we're done. If they match and they're not both $, then we can pop it from the stack and we can advance the input. Jesus Christ. And if it's not a terminal, then it's a non-terminal. So that's this case. So we'll go look that up. So we'll pop that off, and then we'll push those right-hand sides on in reverse order, and off you go. And of course, if you end up looking up an error in here, you would simply report that there's an error, right? Right. So how do we fill this stuff in? Well, let's do one row only, and let's assume that sigma is a1 dot 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 up to an and dollar. And let's say that we have the roll that looks like this. Actually, can I make that an M? And I'll make that an N. So then we can say for A goes to alpha 1, M of A comma something is equal to A goes to alpha 1. What goes there? Well, some of those. Which ones of them? So for which terminals should I pick alpha 1 if I'm trying to parse an A? So if I just So if I took one out and I asked, for which terminals should I pick A goes to plus X of all the possible terminals? Should I pick A goes to plus X if the next thing on the input is a minus? When first of something has alpha 1, other way around. First of alpha 1 has something. First of something is always something because that something is a terminal, right? Remember, this is a terminal. That table is indexed by non-terminal terminal. So this is the second entry, so that's the terminal, right? So the other way around. So in this case, you should probably only pick this if the next thing on the input is a plus. You should pick this if the next thing on the input is a minus. And if it's anything else, then plus and minus, because the first set of this guy is plus and the first set of that guy is minus, we should probably have an error, right? So we can say here that this is little a, where little a is in the first of alpha 1. In general, for alpha I, m of alpha, oops, one thing up here that I forgot. Better take that epsilon out because there's no epsilon column, right? So we'll have to deal with that. We'll come back to that in just a sec. So a comma little a is A goes to alpha I, where little a is in the first of alpha little I. So that's fine. That would actually nicely fill out this table here for this one, and this one. It wouldn't do these two, right? So now we can ask a question. Actually, we need to ask two questions. What about if alpha I is equal to epsilon? And what about if epsilon is indeed in the first of alpha I? That particular case we haven't looked at, but we can do an example on that in just a second. We have looked at the situation of alpha I equals epsilon, and we took one of two options here, and this is actually the type 2 one is the better option because it's easier to formulate and it's more precise. So what we said in that case was, right, if the right hand side is epsilon, then you can put that epsilon rule into any of the columns in which that column's terminal is in the follow set of the left hand side. So if it is epsilon, then we can say m of, well, it's still a because a is the left hand side. I'm going to use a b here, is a goes to alpha I, which is the same as a goes to epsilon because we assume that those two are the same here, where b is in the follow of the left hand side. Now, what about that stuff there? Well, we've already handled most of it, right? Because if epsilon is in the first set of alpha I, well, we took it out there, but we did actually use all the other elements that might have been there. So it's only the situation with the epsilon being in there that's the problem. And if you think about it, if I have some derivation that starts as s, takes a number of steps, gets somewhere, there's an alpha I, and then there's something here. That thing there is in the follow of a, because a goes to alpha I is a rule, right? Because what did this derivation look like in the step before? Well, it probably looked something like that. And that thing there is the same place. So in the epsilon situation, we said, right, let's just take the left-hand side's follow set and use that. We can just do the same in this situation because this is no different. That is also an epsilon. So we'll just say m of a comma b is equal to a goes to alpha I, where that's the case. The only thing I can't say now is that, because I don't know that alpha I is an epsilon explicitly, but I know that epsilon is in the first set. Well, how is that possible? Well, we can try. So we could ask, how can alpha I not be epsilon, but still have epsilon in its first set? Anybody got an answer to that one? Just take a second to think about that. So we're going to need something that looks like this. And what goes here cannot be an epsilon. I'm going to put an alpha there. And I'm going to say alpha is not equal to epsilon. But epsilon, that's an ugly epsilon. But epsilon is in the first of alpha. So can you give me a value, or can you give me something for alpha and maybe some other stuff that will make that all be true? If you don't, I'm going to start singing, and nobody wants that. No, trust me, you don't want that. No, I'm snotty as well, so it's not going to sound nice. No, you don't. Alexis, you really don't want that. No, we cannot vote on that either because you don't want that. Trust me. What would I sing? I don't know. I suppose I should probably let it go. No, so think about it. What can I put? Can I put anything with a terminal in? So I can ask here, um, can alpha have a terminal and also epsilon in its first set? No, it cannot, right? Because that terminal sort of works as a roadblock, right? When we're trying to do the first set thing, where we sort of like, okay, epsilon is in the first set of y1, fine, so we'll take the first set of the next guy, and so on and so forth. But if we have a terminal, then we get to a point where there's no epsilon, and we're done, right? So the answer to that is a resounding no. So it has to consist of just, therefore, it consists of only non-terminals. Right, so couldn't we just pick a non-terminal, a single one? So what if alpha was equal to b, and b goes to epsilon? So if I have a goes to b and b goes to epsilon. Actually, I'm going to say epsilon or x, just so that we get some more fun, right? So if I have that, then isn't it true now that I have a right-hand side that has epsilon in its first set without the right-hand side actually being epsilon? Right, so could I fill in a parsing table for this guy? Well, we can give it a go. I should think it wouldn't be very complicated. I guess this is a little out of proportion. We'll space it a little bit better. There. There. And there. And what do we have? We have X and dollar. We have A and B. Right. What goes here? So let's call this one 1, 2, 3, and 4. And let's do 3 first. So that's M of B comma X is equal to B goes to X, because X is in the first set of X, right? So that's B goes to X. What about number 4? M of B comma dollar. Well, I have two things I can do. It can either be an error, or it can be B goes to epsilon. So should it be an error, or should it be b goes to epsilon? Well, it should only be b goes to epsilon if that dollar is in the follow set of b. Is dollar in the follow set of b? Well, it's in the follow set of a, and a goes to b, so yes. So it should be b goes to epsilon because dollar is in the follow of b, right? So we get b goes to epsilon. Now, what about number one? A comma x. So Nathan, was that an error to this one or the previous one? I just noticed. This one. So I guess we should ask you this question. What's the first of b? So it's x and epsilon, right? And remember, a goes to alpha. M of a comma little a is a goes to alpha for all a in the first of alpha minus epsilon. So there's still that x left. So therefore we get a goes to b there. All right, what about number 3 then? We already done number 3. How about number 2 then? So this one is a goes to b because x is in the first of b. So that's m of a comma dollar. Two options again. So Jonathan says, Nathan, what do you mean for first of b equals x comma epsilon, or first of b equals epsilon comma x? The same. It's the set, right? The order doesn't matter. Or am I misunderstanding your question? No, it's a set, right? It's a set of elements. The order doesn't matter because you're quantifying over it here, right? You're saying for all, so you're just taking them out, and then whatever you take out chooses the column for you. Now, if we look at this guy here, we said, right, we threw away that epsilon guy there, but now we have got to be a little careful here, right? Because epsilon is in the first of b, we have to say that m of a comma little b is a goes to, and now you have to be careful not to be tempted to say a goes to epsilon, although it would parse correctly. It's not correct. We need to let b go to epsilon, so we'll go that for all b in the follow of the left hand side, which is a. So what is the follow of a? Well, I think it's just dollar, isn't it? So we get a goes to b because dollar is in the follow of a. So we get a goes to b there as well. As I said, if you had put a goes to epsilon, it would have parsed in exactly the same way, because a goes to b on the dollar forces b goes to epsilon the next time. But it would have to be um, one of the right hand sides. We don't have a right hand side here that has an epsilon, so you can't technically put an epsilon there, right? Now, see algorithm 10. That's the one that fills it up. And then of course we need one other thing, any blank cell in M gets an error rule, right? So let's try another one. And that's exactly the one that we just had before. I'll just make sure we didn't just do that one. I'm getting old. I don't remember what I've done. Oh, that's the one we just did, isn't it? Yeah, there's no need to do that again because we already did it, right? Yeah, this is actually example 4. How can I not remember that? Embarrassing. Okay. Can I so is this erase this stuff here. Is this all right, everybody? This is not so, it's not too hard, right? So I wanted to be a little bit more pedantic about filling in the table because so we said something like for A goes to alpha. We said that the first part was that M of A comma A is A goes to alpha for all A in the first of alpha minus epsilon. And then we said if epsilon is in the first of alpha, then M of A comma B is A goes to alpha for all B in the follow of A. That's how we filled it in. So we note here either we only use a first set without an epsilon. So if epsilon is not in the first set, then we would never do this. Therefore, we wouldn't have to take it out of there, and we would only do this. Or we use a first set minus an epsilon plus a follow set. Could I define a function that would give me that as one set? Because if I look at what I'm doing here, I'm setting an entry in this row of the parsing table in both cases, and I'm setting it to the same thing. I'm just quantifying over different sets. So in one situation, it's for all A in the first of alpha, or in the other one is for all A in the first of alpha minus epsilon plus all the elements in follow of A. So what if I defined, maybe not in red, that's so aggressive. I'm going to define a new set, and I'm going to call it a predict set. And we're going to define it in the following way. One of two things can happen. Either epsilon is not in the first of alpha, or epsilon is in the first of alpha. Those are basically the two options that I have, right? What happens if epsilon is not in the first of alpha? Well, then I'm going to make this predict set just be first of alpha. Well, that's exactly what we did here. We said, well, if epsilon is not in there, then we're not going to do this, and we're just going to use this, which without the epsilon, which is not there anyways, is just that. So if epsilon is not in the first of the right-hand side, now my predict set is exactly the set that I'm going to fill in the M table with. Okay. If it is in, well, then I need the first set, but I take it out, and then I union onto that the follow of the left-hand side. Now, we can simply say for A goes to alpha, M, A comma little a is A goes to alpha for all A in the predict set of A goes to alpha. Because whatever this comes out to be is either this or that. If epsilon is not in there, then it's just that. And indeed, if epsilon is not in that first set, then we don't do that when we fill in the table. We just use that. Well, that's exactly this. If epsilon is in the first set, we take it out of there, and then we add on to that. Well, there it is, first of alpha minus epsilon plus the follow of A. So now I can write that as just sort of a simple thing there. And that's nice because that I can actually use to say something about LL1-ness of this grammar. So note also that G, so well, let's say let G be a context-free grammar. G is LL1. Would you all agree with me that G is LL1 if and only if no cell in M has more than one entry? I mean, what would happen if a cell in a table like this had two entries? So let's see. We can just do a small little example that says A goes to X, Y, or X, Q. If I look at the table, I have A here and X here. Then I would get A goes to X, Y, and I would get A goes to X, Q there. And that is a double entry because first of X, Q intersected with first of X, Y is not empty, right? And we know that they have to be empty for things to be LL1. And we can see if they're not empty, if there are two right-hand sides of the same left-hand side that intersect not empty when looking at first sets, then we get dual entries. But if I can fill in this table using whatever rules we've decided, in particular those things with the epsilons, without making any double entries, then no matter what I see on the input, and no matter what non-terminal I have on top of the stack, I will always be able to make either the right choice, the next step in a derivation, or produce an error. So hopefully you'll be okay with the statement that G is LL1 if and only if no cell in M has more than one entry. Right, how were those cells filled in? Well, they were filled in using the predict sets. So that means that if instead of using first sets when I do these pairwise disjoint tests, if I use my predict sets, then I know that if no predict sets intersect non-empty, No. Then I know that if all the predict sets intersect non-empty, sorry. Then I know that if my predict sets intersect empty, then the grammar is LL1. Because if they didn't intersect empty, then they would have something in common. And whatever it is they have in common would give rise to a double entry. And we've just said that there were none of those. So we can basically here now say that this is the same as saying for all left-hand sides A, and their right-hand sides, I'm going to call them alpha 1 dot, 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 alpha n, no two right-hand sides of A have anything in common with respect to their predict sets. That is for all I and j where 1 is less than I and j is less than n, and I and j are different. If I look at the predict set between A alpha I and the predict set of, then I get the empty set. And you can hopefully see now why this arrow, well, we didn't have that before when we just looked at first sets, because when we just looked at first sets, we just took that set when we filled in the table. We didn't take that into account. But can we create a grammar that has that has this problem that shows that we get in trouble? So maybe we can. What if we do something like A goes to a y or x, and x, or do we have to think a little bit now? What if I did something like this? Fill in my table. I have a and x, and I have a, b, and dollar. If I compute first sets, I get an a, b epsilon, epsilon, b. First, sorry, we need some follow sets. Follow of b is little a. Follow of capital A is, sorry, follow of b is, there's no b at all. That's an x. Follow of x is follow of a, which is little a and dollar, and follow of a was little a and dollar. So if I try filling this in now, surely here we get a goes to a y. Then I get a goes to x there, but also because epsilon is in the first of x, we get m of a comma little, I'm going to use something else here, little y is a goes to x for all little y in the follow of the left hand side, which is a, and that follow set is a and dollar. So I would get a goes to x there, and a goes to x there. So that grammar is not LL1, because we got a double entry using the rules for filling it in. Yeah, that was right on time. I'll stick around. This time I won't actually log out like I did last time for a little while. If anybody has any questions for the for phase 3, but what I'm going to do is I am going to